All right, upper school. I'm going to be going over the lesson opener and exploration one for your HMH digital textbook assignment. Make sure you're checking Jupyter. There's also an Ed puzzle assignment that's due on Friday. I'm really glad everyone has internet so we can keep it up. I'm really, really proud of you guys for doing your best to work hard while we're away from each other. It really is going to benefit you in the long run, especially those of you going to high school, because this is actually a pretty good simulation of a lot of things that are going to be happening in high school. A lot of the work does happen outside of school, so get ready. So we're going to be talking about changes in energy. This is the next lesson we would have been talking about. We are going to be looking at different types of potential and kinetic energy, and then different versions of that. Again, when we get back, hopefully sooner rather than later, we will then apply this knowledge to create some pretty cool inventions and ways to make to conduct electricity. So this is a cool picture of a dam. It's called China's Three Gorges Dam, the world's largest hydroelectric power station. Look at that word, hydroelectric, water electric. It captures energy from water and transforms it into electrical energy. So transform is going to be a really important word for us. That is changing one form of energy to another. So watch the video. We're going to have these videos pop up, and I'm just going to kind of explain them. There's also closed captioning, so you'll be able to hear what they're saying, but I'll chime in if I think it's important. So it says hand-powered flashlights are useful tools in an emergency. They do not need replaceable batteries or other sources of electric power. Instead, the user turns a crank on the side of the flashlight. This causes the light bulb in the flashlight to light up. And before I keep going, I did want to mention, like, you can use these videos in a couple different ways. You can kind of play it while you're doing the hard copy version. You could kind of like split screen, put this on one half of your screen and put the digital textbook on another, or you can use your cell phone and have this video on your cell phone while you have the book on your computer. A lot of different ways you can do it, but I thought it would be helpful to record a little lesson for you guys. So if you look at this, they do is we have one of these at school too. So the light turns on whenever you crank the flashlight. So there's a lot of different types of energy going on here. When you stop, the light dims. Okay, so how would you define the flashlight as a system? What are its inputs and outputs? What are parts of the system? So inputs are things that go into the system. Outputs are things that go out. So input of this system would be the person thinking the output of this system would be the light. And believe it or not, the input and the output here are both types of energy. The crank has energy when it is turned. What other types of energy might the flashlight have when the light bulb is on? So we have electrical energy. I wish you guys were here so I could call on a bunch of people right now. Has electrical energy. It also is giving off some light energy. Anytime there is light energy in a flashlight, there's also some heat. Right, so lots of transformations there. So that's the lesson opener, and then we're going to go through exploration one. Identifying different forms of energy. So processes and technologies that require energy are all around you. We did that energy detective assignment. That was pretty cool. You guys did a good job of finding all the ones that were in our school. The movement of a clock's hands, the light from light fixtures, and the sounds made by electronic devices are all results of changes in energy. Apply our understanding of energy allows us to do everything from launching rockets to cooking food. So here's some carnival rides. You can observe many different types of energy. Take a look here. All right, I'm going to pause it there. So what types of energy can you identify in the video? Again, I'd be calling on a bunch of people here, but there's definitely light energy. We see the movement of this Ferris wheel and this really scary ride that I would not go on. That's definitely kinetic energy. But there's a lot of things that have height here, right? So there's potential energy. Actually, that's gravitational energy. If you got any of these, that's fine. Again, I'm grading these on effort, so just keep up the hard work. Anything else here? Again, we have lights, so there's probably some heat, right? These lights are powered probably by electrical energy. That's some pretty cool stuff there. Objects in motion. Here's a bowling ball. A bowling ball rolling down a lane towards the pin has energy. Evidence of this is the force that would be required to stop the rolling ball. A force was also used to send it rolling towards the pins. The energy that an object has due to its motion is called kinetic energy. All moving objects have kinetic energy. A bowling ball traveling down a lane, a skateboarder rolling down a ramp, and a water rushing down a river all have kinetic energy. Kinetic energy and mass. A bowling ball has a much greater mass than a tiny ball used in a pinball machine. A bowling ball has a mass of 6 kilograms. I'm going to highlight that. A pinball has a mass of 0.08 kilograms. Think about what would happen if you rolled these net balls down the same bowling lane at the same speed. Would both balls have the same amount of energy? Imagine both balls striking the center pin after they roll down the lane. What would happen? So, small, big, bowling pins, what do we think would happen? Well, I predict that the pinball would have energy bowling ball. The kinetic energy of an object depends partly on its mass. Notice partly. It's not all about the mass. There's other things that go into it. In the example above, the bowling ball has more kinetic energy than the pinball. They are traveling at the same speed, but the bowling ball has more mass. You can see that the bowling ball has more kinetic energy because more force is needed to stop the rolling bowling ball. The two balls with different masses move at the same speed, have different amounts of kinetic energy. Now think about how different speeds might affect kinetic energy. So this time we're going to talk about speed, not mass, because that's important too. So it says two bowlers each roll a 6 kilogram bowling ball. They're both 6 kilograms. I'm going to highlight that. Come on. No, maybe not. One ball rolls very fast, the other ball rolls slowly. Predict what will happen when each ball strikes the pins. What does your prediction tell you about how much energy each ball has? The faster bowling ball most likely knock down more pins. Of course, you have to be accurate too. Say that they're both accurate. The slower one down because, and you guessed it, it does not have. Kinetic energy is directly proportional. That means it correlates to the mass of an object. It is also proportional to the square of the object's velocity. A ball traveling at a fast speed will require more force to stop its motion than it would if the ball were moving more slowly. Therefore, the ball has more kinetic energy when it is moving faster. Stored energy, potential energy. A ball at rest at the top of a hill does not have kinetic energy. So if it's not moving, no kinetic energy. As it rolls down the hill, it gains kinetic energy. Where does the kinetic energy gained by the ball come from? When the ball is at rest at the top of the hill, its position gives it a potential to begin rolling and gain kinetic energy. So the higher it is up there, the more energy it has potentially. The energy stored in an object due to its position or condition, that's good for chemicals, is called potential energy. For example, increasing the height of this ball's position will increase its potential energy. As the ball rolls down the hill, its potential energy decreases. Its potential energy is as low as possible at the bottom. In the carnival game in the photo, the player must roll the ball with enough speed to get it over the hill on the track. Think about how the ball's energy changes at different points along the track. At the top of the hill, the ball's potential energy is at its maximum. As the ball rolls downhill, its kinetic energy increases, its potential energy decreases. We did a simulation for that that you guys did really well on. At the bottom of the hill, the ball's potential energy is at its minimum, and its kinetic energy is at its maximum. The ball slows down as it rolls uphill. It speeds up as it rolls downhill. As the ball loses potential energy, it gains kinetic energy. When the ball gains potential energy, it loses kinetic energy. The total energy that the ball has does not change. Like matter, energy cannot be created or destroyed. That means that the total amount of energy in a system does not change unless energy is added to it or removed from it. This is known as the law of conservation of energy. Just as a ball on a hill will naturally roll downward, the water at the top of a waterfall will flow downward. A pendulum released from the top of its arc will swing downward. Before they move downward, the ball, the water, and the pendulum have potential energy because of their positions. The potential energy of an object due to its height or its position relative to Earth's surface is called gravitational potential energy. The higher an object is, the greater its gravitational potential energy. For example, water at the top of a waterfall will have its greatest gravitational potential energy because its height above the Earth's surface is greater than it's at the bottom of the waterfall. So we have water flowing downhill. Its energy changes as you move from the top to the bottom. How can you describe the general behavior of objects undergoing changes in potential energy? So objects tend to move from places where they have more potential energy to places where they have less potential energy. In other words, changes of energy tend to result in a decrease in potential energy. Okay? Imagine holding a ball in the air. If you drop it, the ball will fall to the ground. It falls due to the pull of Earth's gravity. All objects tend to move from places where they have high gravitational potential energy to places where they have low gravitational potential energy. This means that balls do not roll uphill on their own. Pendulums do not spontaneously swing upward. Water does not flow up a waterfall on its own. However, you can make objects move upward by adding energy to them. So we're going to cover a bunch of different forms of energy. Energy comes in a lot of different forms: thermal, sound, electromagnetic, electrical, and kinetic. Chemical energy, nuclear energy, gravitational potential energy, and elastic potential energy are all forms of potential energy. All forms of energy are expressed in units of joules. Mechanical energy is described as an object's ability to move or do work on other objects. It is the sum of the potential energy and kinetic energy of an object or a system. For example, a person swinging a hammer is providing kinetic energy to the hammer. The hammer does work on a nail. An object's mechanical energy can be all potential energy. It can also be all kinetic energy. It can also be a combination of the two. So mechanical energy is you just add the potential of kinetic energy. So there's other forms of energy that you see every single day. Here are some examples. Electromagnetic energy is light energy here in the form of light bulbs. We have some thermal energy in an oven. We have sound energy in the bell. We have electrical energy in all these appliances. Chemical energy, which is some of your favorites in this beaker, and so on. So we're going to jump down here. Okay. So objects tend to come to a rest at a position of lowest potential energy. Think of a machine or system that works against this tendency. Describe how kinetic energy is needed to increase the systems of potential energy. So this is like an old blueprint about mechanical energy. And one that comes to mind for me is a roller coaster. Moves a cart upward. It does this carrying the cart up this conveyor belt powered by. Might your machine or system be improved? What constraints might be involved in its design? So if I'm designing a roller coaster, I need to make sure that I don't waste as much energy. That's why you usually only see on roller coasters the highest hill is the first one, because you don't need to use any energy after that first one. You just use potential and kinetic energy over and over again. So for a roller coaster, the first hill needs to be the way. Do not need to add any more kinetic energy after. That's for us to save money, and money is always a constraint. So that's it for today. We'll be back tomorrow for the second exploration. We'll get better at these as we go on. I do want to kind of maybe not read everything and just kind of stick to summarizing some things. So bear with me, but take care.